Hello, everyone. My name is Kubo, and today I would like to talk to you about mathematical optimization plus artificial intelligence equals MOAI. MOAI is a term I coined to represent the fusion of mathematical optimization and artificial intelligence, as the name suggests. As you can see in this Venn diagram, MOAI resides in the intersection of mathematical optimization and artificial intelligence. Here, mathematical optimization is a subset of a broader optimization domain, while machine learning is a subset of artificial intelligence. Our target is the fusion of optimization and machine learning, but for brevity, I refer to it as MOAI. As indicated by the real-world problems in the lower right corner of the diagram, our target is not merely the theoretical integration but the development of fusion technologies that solve real-world problems. In other words, MOAI is the integration of machine learning and optimization to solve practical issues. In the following sections, I will explain the classification of MOAI, propose some new methods, and discuss their applications. Before diving into the main topic, let me introduce the abbreviations that will be used in this presentation. MO stands for mathematical optimization. O refers to the broader concept of optimization. ML stands for machine learning. RL, which is a part of machine learning, stands for reinforcement learning, which has a closer relationship with optimization. MPC stands for model predictive control. RL, MPC, and dynamic programming and optimization are essentially targeting the same type of problems. Research on MOAI has rapidly advanced in recent years, akin to the explosion of ideas during the Cambrian period. The primary purpose of this lecture is to categorize and organize these studies. Here, I classify them into 7 patterns. This classification is provisional, and some research may fall into multiple categories. Please consider it as a guideline for organizing research. Let me explain the classification of fusion patterns using the diagram. In the upper left, we have what I call ML first, MO second. As the name suggests, it involves conducting machine learning first, followed by optimization. Typically, machine learning is used for predictive analytics, while optimization is used for prescriptive analytics. Since it is natural to perform optimization after making predictions, most traditional integrations fall into this category. In the upper right is the opposite pattern, MO first, ML second. This involves using the results of optimization for subsequent machine learning. Although this case is rare in practice, I include it as a category. In the middle left, we have ML for MO, where machine learning assists optimization, as the name suggests. Here, optimization is the central focus, and machine learning supports it from the periphery. To the right of that is the opposite pattern, MO for ML, where machine learning is the central focus, and optimization assists it. The next category, mutual integration and optimization theory, lies to the right of that. The reality is that machine learning is fundamentally optimization. Hence, optimization theory is deeply involved in machine learning. For example, by formulating machine learning models as mathematical optimization problems, various insights can be gained. In the lower left, we have the integration of reinforcement learning and model predictive control. These fields were independently studied in different domains, but dynamic programming in optimization, reinforcement learning in machine learning, and MPC in control theory are all based on the same framework. Recently, research on integration across these fields has been advancing. In the lower right, we have research that uses large language models, LLMs, like ChatGPT or Claude to assist in mathematical optimization modeling. This field is still new and developing, but I would like to include it as a category. Please note that this classification is not exhaustive but rather a matter of convenience. Some studies may belong to multiple categories, and others might not fit into any of them. This is merely a guide to help organize the rapidly growing field of fusion research. Now, let's proceed to the agenda and introduce each topic in turn. Pattern 1 is ML first, MO second. This is the most classical and natural approach, where ML is used to make predictions, followed by MO. The first approach involves using ML to make predictions with the given data, approximating some function, and solving it by incorporating the approximated constraints or objective function into MO. This can be further divided into embedding the ML predictive model directly into MO as a mathematical formula, treating ML as a black box for optimization, and approximating the ML predictive model as a function that is easier to solve under realistic assumptions for MO. The second approach is to perform preprocessing, such as clustering or dimensionality reduction, with ML, before applying MO. I will explain these approaches in detail in the following slides. Limited ML predictive models can be embedded directly into MO as mathematical formulas. This approach is called constraint learning. Constraint learning can be easily implemented using Gurobi ML, an open-source library provided by Gurobi, a commercial solver company. Currently supported ML models include linear regression, quadratic regression, logistic regression, neural networks, decision trees, gradient boosting, and random forests. However, the neural networks are limited to fully connected layers with ReLU activation functions. As shown in the diagram at the bottom right, after learning the mapping from feature vector X to target Y with the ML model, it is embedded as a formula into the mathematical optimization model for solving. However, when embedding ML models, integer variables are used, making the mathematical optimization problem more complex and sometimes unsolvable. Therefore, this approach is limited to simple ML models. If you want to use a complex ML model, the recommended approach is to treat ML as a black box for optimization. This involves treating ML as an oracle for black box optimization, which works with any ML model, but it takes a long time for optimization. Therefore, this approach is limited to relatively small and simple optimization problems. So, how can complex ML models be incorporated into large-scale mathematical optimization problems? This is an approach I frequently use to solve real-world problems, where the ML predictive model is approximated as a function that is easier to solve under realistic assumptions for MO. First, after training with any ML model, a large amount of training data is generated. The diagram at the bottom right shows an approximation of the actual function, with the horizontal axis representing transportation volume and the vertical axis representing transportation costs. After performing automated ML on the actual transportation data, transportation costs for various volumes are calculated as the blue line. Based on this, the function is approximated as the red line, satisfying practical axioms. Transportation costs by location and transportation mode are assumed to be monotonic non-decreasing, i.e., costs do not decrease as weight increases, continuous, i.e., no sudden changes, concave, i.e., unit costs decrease as weight increases, and pass through the origin, i.e., no cost when nothing is transported. This piecewise linear approximation satisfying these axioms can be easily computed using a mathematical optimization model. However, in practice, actual transportation costs may be step functions, like taxi fares. In other words, the assumption of continuity might be violated in real-world problems, but for the sake of ease in mathematical optimization, continuity is assumed. As you can see, applying this approach requires knowledge of real-world problems, mathematical optimization, and machine learning, and you need to design functions according to the problem, which is a drawback. Using ML for preprocessing before applying MO is also a natural fusion method. This example is called the logistics network design problem. The goal is to optimize transportation routes and warehouse locations from 3 factories to candidate warehouse locations and customers. As shown in the upper diagram, let's assume there are 1,000 customers. Including all 1,000 customers directly into the mathematical optimization model is not a very sensible approach. In practice, machine learning techniques like clustering are used to aggregate customers into about 50 clusters. However, traditional ML methods like k-means minimize the sum of squared distances, so in this case, clustering is done such that the total demand per cluster is below a certain threshold and the sum of Euclidean distances is minimized. This is shown in the lower left diagram. The lower right diagram shows the optimal transportation routes and warehouse locations for the aggregated customers. Thus, using machine learning as a pre-processing step for mathematical optimization is a practical choice. There are also various other methods under the ML first, MO second pattern. Classical stochastic optimization and its variations can also be considered part of this category if viewed as applying mathematical optimization after processing data. In classical stochastic optimization, the probability distribution of random variables is estimated based on data. There are issues with the difficulty of estimating the actual distribution, and the optimization itself can become challenging. In robust optimization, the uncertainty set of random variables is estimated based on data. Under certain assumptions, optimization becomes relatively easy, but since the worst-case scenario within the uncertainty set is considered, the solution can be overly conservative. In distributionally robust optimization, the ambiguity set of distributions is estimated based on data. This approach is considered a hybrid of stochastic optimization and robust optimization. The ambiguity set can be generated using machine learning. Additionally, adjustable models that consider recursive variables defined as affine functions of random variables can be constructed. Let's consider the example of the stochastic shortest path problem. You commute by car from home, starting point S, to the university, destination T. There is a route via the highway, S1, and 1T, that takes 2 hours in the best case but can take 6 hours if traffic is heavy, which happens with a probability of 1/2. You leave home with a 5-hour margin before your class begins, but you want to reach the university as quickly as possible. What route should you choose? In a deterministic optimization where we take the expected travel time, the path S1, T would be the optimal choice, with an expected travel time of 4 hours. However, if travel time is considered probabilistically, there is a 1/4 chance that you would be late by 1 hour. The only path that guarantees arrival within 5 hours is S2, T. This is the optimal solution in a stochastic optimization that minimizes the probability of being late, resulting in an expected travel time of 5 hours, which is 1 hour longer than the deterministic optimization. Another possible route is to take the highway initially and then switch to local roads, following the path S1, 2, T. This route has a half chance of being late and an expected travel time of 4.5 hours. Now, let's consider a strategy that allows you to make decisions based on real-time information rather than pre-deciding the route. For instance, after reaching point 1, if the travel time from S to 1 is 1 hour, you proceed from 1 to T. If it's 3 hours, you switch to the route 1 to T. This is a dynamic decision-making process, or an adaptive strategy. Assuming the travel time on the highway follows the same distribution, the expected travel time is 3.75 hours with a half chance of arriving 30 minutes late. This is the optimal policy for a maximum travel time of 5.5 hours. Now, consider a scenario where you have past weather and travel time data. If we assume the weather forecast is accurate, the goal is to predict travel time and choose the optimal route based on this prediction. We refer to the weather forecast as context, and denote the travel time conditional on this context as hat-C. Note that simply minimizing prediction error based on the context is equivalent to minimizing the expected travel time. By using a loss function that measures the difference between the predicted and actual costs, we can train a machine learning model to generate good predictions that lead to better optimization outcomes. This approach is known as smart prediction then optimize. Let X** represent the optimal solution for a given travel cost C. The optimal value when C is known is denoted as Z**C. On the left side of the figure, we have the optimal solution for the predicted travel time C_hat when the weather is sunny. On the right, we have the optimal solution for the actual travel time C when C equals 3. The difference in optimal values is the loss function of smart prediction then optimize, SPO, which calculates to 1. By training the model to minimize this loss, we can achieve better predictions that result in better optimization decisions, rather than just minimizing prediction error. However, this loss function is non-convex, making it difficult to train. To address this, a method using SPO plus loss, which is an upper bound of the SPO loss and a convex function, has been proposed. This makes training easier. Additionally, the estimation then optimize approach has been suggested. This method involves predicting travel time from the context and generating scenarios for stochastic optimization. It can be combined with other approaches like CVAR minimization, chance-constrained optimization, or robust optimization. Formally, we can describe this process as follows: predicting the values that minimize error and then optimizing is known as predict then optimize. Incorporating optimization within machine learning is what we call smart predict then optimize, where we use the SPO plus loss as the loss function. Various other variations have also been proposed, and a library called PYEPO has been developed to handle these unifiedly. Estimation then optimize has practical applications. For instance, a study conducted by Bertsemes and his team at MIT used Google Trends as context to predict CD sales, optimize inventory based on scenarios generated through machine learning, and successfully reduce inventory levels. Another package, RSUM, has been released to model distributionally robust optimization and context-aware stochastic optimization. It extends deterministic optimization models by adding random variables, uncertainty sets, and ambiguity sets. So far, I've explained the ML first, MO second pattern. This is a natural approach with many applications, though it has been mainly applied to relatively simple problems like inventory optimization. Future research and applications are expected. The second pattern is MO first, ML second. This approach is somewhat unconventional, as it involves performing optimization first and then using machine learning to make predictions. Here's an example: consider a delivery optimization problem where past customer demand is known. Each day is associated with features like the day of the week or special events. The goal is to predict the number of trucks needed to meet unknown customer demand. You can perform delivery optimization on past data to determine the minimum number of trucks needed for each day, then use machine learning to predict the number of trucks based on the features of past days. This is an example of the MO first, ML second approach. The third pattern is ML for MO, where machine learning assists optimization. In this case, optimization is the core task, and machine learning supports it. One simple application is using machine learning to choose the algorithm, set parameters, or select the method for solving an optimization problem. A more complex application involves using machine learning within optimization itself. For example, machine learning or reinforcement learning can improve branching rules or cutting planes. Directly solving combinatorial optimization problems using reinforcement learning is also part of this category. When provided with a series of problem instances, optimization can be used to generate pairs of problem instances, feature vectors, and solutions, targets. By learning from these with machine learning, you can directly obtain solutions with machine learning. For new problem instances, using machine learning to accelerate optimization is an innovative idea. Examples include MIP Learn, where ML provides hints or constraints to speed up optimization, Optimization Proxy, where ML outputs an approximate solution that is corrected into a feasible solution, and Optimization Voice, where ML predicts the values of integer variables and equality constraints to generate solutions. This diagram illustrates the 4 types of ML for MO concepts. The categories include selecting algorithms or parameters with ML before optimization, integrating ML within the optimization process, solving combinatorial optimization problems with reinforcement learning, and using ML to directly obtain solutions. When a series of problem instances with numerical values is provided, learning the performance of various optimization methods in advance and selecting methods or parameters with pre-trained ML models can enhance optimization performance. Developing this idea further, we can design AutoOpt, an automated system that continuously learns the performance of multiple optimization models and automatically selects the best one for continuous optimization system operation. By choosing from the candidate optimization models based on learned performance with appropriate probabilities, you can ensure that solver selection always makes efficient use of computational resources, even when problem instances change. Here's an example of using ML within optimization. A study by DeepMind and Google Research applied graph deep learning to general MIP, mixed integer optimization problems, to improve branching rules and heuristics like diving with deep learning or RL. They reported success in improving the performance of the open-source MIP solver SCIP, but it remains to be seen whether these methods can enhance the performance of highly tuned commercial solvers. Research on solving combinatorial optimization problems with reinforcement learning is also active. RL4CO is a library based on PyTorch's reinforcement learning library TorchRL that can solve various combinatorial optimization problems. It uses state-of-the-art attention models and proximal policy optimization, but in small to medium-scale experiments on the traveling salesman problem and its variations, it only slightly outperforms greedy algorithms. It also supports scheduling problems, but again, the results are only marginally better than dispatching rules. A challenge remains in scaling these approaches to large problem instances. By training machine learning models on past problem instances and solutions, you can accelerate optimization. Here are some methods for doing so. The first is called MIP Learn, which predicts the distribution of solutions with ML, then uses that information to provide initial solutions, variable hints, or additional constraints to the optimization solver. An application of MIP Learn can be seen in the research by Xavier and colleagues. They applied this method to the unit commitment problem, using k-nearest neighbors or SVM to fix variables based on training data. The unit commitment problem involves optimizing power plant output, where problem structure remains consistent, making it easy to define the closeness of problem instances, allowing k-nearest neighbors to be applied. A general-purpose package for combinatorial optimization problems is also available. Examples include the traveling salesman problem and the knapsack problem, where the structure is the same, and only the numerical information changes. The experimental results on the bottom right of the slide demonstrate that MIP Learn can be used for both exact and approximate solutions. Compared to solving the MIP problem without MIP Learn, leftmost, the methods using MIP Learn, middle and right, achieve significant speed improvements. The following study was conducted by Pascal van Hentenrijk and colleagues at Georgia Tech, and it focuses on an approach called optimization proxies. Since deep learning struggles with directly handling constraints, it is generally difficult to train a model to output optimal solutions directly. The basic idea here is to train the model to output infeasible approximate solutions, called proxies, and then transform these into feasible solutions using repair layers. The researchers applied this approach to power transmission flow optimization, designing 2 repair layers specifically for this purpose. Additionally, they used Lagrange relaxation to adjust the parameters to satisfy constraints. The power transmission flow problem, characterized by a constant structure and the need for real-time responses, serves as an effective example of where optimization proxies can be advantageous. The next study was conducted by Bertsemas and colleagues at MIT and is referred to as the voice of optimization. This approach involves learning the inequality constraints that become equalities and the values of integer variables instead of the optimal solution itself, through decision trees or neural networks. With this information, the solution can be quickly approximated by solving a system of linear equations, making the process highly efficient. This method has also been packaged for public use, demonstrating its effectiveness in applications like inventory optimization and the knapsack problem. Consider a scenario where instances of mixed integer optimization problems with slightly varying parameters are provided online. Mixed integer optimization problems are composed of integer variables, real variables, and constraints. During the training phase of a neural network, the model learns the integer variables and the constraints that become equalities in the optimal solution. The researchers term this information as the voice of optimization or strategy. When a new problem instance is presented, multiple strategies are predicted using the trained neural network, and several approximate solutions are derived by solving the system of linear equations. The best solution among them is then selected, allowing for a fast approximation of a good solution. Here is a schematic representation of the 3 approaches: MIP Learn, optimization proxies, and the voice of optimization. All of these methods share a common challenge: directly learning feasible solutions through machine learning is difficult. As a result, each method involves learning some form of surrogate information, from which the solution can be derived. In MIP Learn, hints for the solution are learned and used to derive the solution via a mathematical optimization solver. In the optimization proxies approach, an infeasible approximate solution, called a proxy, is learned, and the final solution is obtained through a repair layer. In the voice of optimization, the values of integer variables and the inequalities that become equalities are learned, and the solution is derived by solving a system of linear equations. All of these methods assume that the problem structure remains constant while only the numerical values change. Additionally, it is evident that these methods include problem-specific components and are not universally applicable. For general mixed integer optimization problems, combining these three approaches can help to mitigate each approach's weaknesses. First, the optimization proxies idea is used to train the model to output infeasible approximate solutions. Simultaneously, ideas from MIP Learn and the voice of optimization are employed to learn solution hints, fixable variables, and constraints that become equalities. Next, a repair optimization is performed using this information to obtain feasible solutions. By incorporating distance constraints from the infeasible approximate solutions, fixable variables, and equality constraints, the process can be accelerated. However, many real-world problems do not satisfy the assumption of a constant structure with only numerical changes. To apply these methods to problems with different structures and to achieve speedup by leveraging past problem instances, a measure of similarity between problem instances and solutions is required. Various ideas, such as those shown here, can be considered for this purpose, but more fundamental research is necessary. Later, I will discuss similarity in greater detail. The three approaches, MIP Learn, optimization proxies, and the voice of optimization, are based on a common idea, which is generalized here as the Encode-Decode method. This method consists of an encoding, which is something from which the solution can be recovered, and a decoder, which is an algorithm to quickly recover the solution based on the encoding. The encoding must be designed to have a simpler structure compared to the solution itself so that it can be easily learned by the machine learning model. MIP Learn, optimization proxies, and the voice of optimization can be interpreted as special cases of the Encode-Decode method when the encoding and decoder are interpreted as shown in this table. By leveraging the flexibility of the Encode-Decode method, it can be applied to a broader range of problems. For example, in scheduling problems, if the order of job release and job modes are used as the encoding, the solution can be easily decoded using a classical heuristic called the active schedule generation scheme. Even if the encoding is limited to just the order of job release, the solution can be decoded using a scheduling optimization solver we developed called OptSeek. OptSeek is designed to quickly approximate the solution when the order of job release is provided as an initial solution. In vehicle routing problems, using pre-tours as the encoding can also lead to the design of fast decoders. This concludes my explanation of the patterns in ML. Now, let's summarize the challenges in ML for MO. First, it is necessary for the training and test problem instances to be close to each other. Therefore, it is not very effective in cases where entirely different problem instances arise each time. Additionally, it was effective when the problem structure remained the same and only the numerical values differed. Consequently, even in past studies, applications focused primarily on the power sector, where the structure remains constant while the numerical values change. To apply these methods to a broader range of applications, it is necessary to define similarity between problem instances with different structures, which I will discuss in more detail later. Pattern 4 is classified as MO for ML, where mathematical optimization assists machine learning. The primary focus here is on machine learning, with mathematical optimization playing a supporting role. For example, machine learning with constraints on parameters can be formulated and solved as an optimization problem. Additionally, there are studies where mathematical optimization is used for feature selection in machine learning or to construct optimal decision trees. A method for performing classification and regression using integer optimization was proposed by Bertsemas and colleagues. The figure in the lower right corner illustrates a regression analysis performed on discontinuous data using piecewise linear functions, which can be obtained through integer optimization. Decision trees, a classical model in machine learning, are constructed using optimization. While classical CART uses a greedy approach, other optimization methods can build better decision trees. The figure in the lower right corner shows a method of probabilistic branching using continuous nonlinear optimization. Bertsemas and colleagues proposed a method to construct optimal classification trees using mixed integer optimization. This approach allows for the creation of decision trees with high interpretability, although it has the drawback of potentially requiring extensive computation time, depending on the scale. Subsequently, various methods for speeding up this process have been proposed, including selecting data subsets, formulations specific to binary classification, flow formulations, the application of Bender's decomposition, formulation improvements, the application of constraint optimization, approximate optimization, and the use of data mining techniques and dynamic programming. However, many of these methods are suited for categorical data, and continuous data may require appropriate discretization. Open-source packages for optimal decision trees, such as those shown here, have been made available. Note that mathematical optimization-based methods require a separate mathematical optimization solver. MO for ML is a powerful tool when used correctly, applying mathematical optimization techniques to machine learning. For optimal decision trees, several fast methods have been proposed for categorical data, but for continuous data, it is necessary to either apply appropriate discretization or use approximate optimization. Pattern 5 involves cross-pollination at the foundational level of optimization theory. While machine learning and optimization are studied as separate fields, the optimization aspect shares the same fundamental goals. Optimization in deep learning, for example, involves the optimization of non-convex nonlinear functions. The momentum used in this context is known in the optimization field as Nesterov acceleration. While deep learning typically follows an experimental and practical approach, such as the fit one-cycle method, the optimization field focuses on theoretical convergence proofs. Furthermore, mathematical optimization is used to interpret machine learning models mathematically, providing insights that lead to improvements, convergence guarantees, or new model ideas. Pattern 6 involves the fusion of dynamic models, particularly those dealing with dynamic optimization problems where future information is either unavailable or uncertain. In optimization, this area has been studied under names such as dynamic programming, DP, NeuroDP, and approximate dynamic programming. In the control field, it is known as model predictive control, MPC, and in artificial intelligence, as reinforcement learning, RL. These can be described within the same framework. Additionally, multi-period stochastic or robust optimization deals with similar issues, with affine recourse function adjustment inspired by linear feedback and control. Recently, research has increasingly focused on blending these methods across disciplines. Since DP and RL are likely familiar to you, I'll briefly explain MPC and approximate DP. Model predictive control MPC, as the name suggests, involves making predictions and using optimization to control the system. As shown in the diagram in the lower right, the basic framework involves repeatedly solving optimization problems for a planning period from the current time into the future, to control the system. In the optimization field, this is also known as the rolling horizon approach. Since the objective is control, the optimization is performed by solving a convex quadratic optimization problem for stability. Next one is approximate dynamic programming. This approach has been applied to various fields by Powell of Princeton. In simple terms, it is a fusion of dynamic programming, reinforcement learning, and mathematical optimization. The diagram illustrates its application to the long-haul transportation problem, where the movement of long-haul trucks is optimized through dynamic transport planning by repeatedly solving a one-period transportation problem. To account for the uncertainty in future demand, the value function, a fundamental principle of DP, is used. One idea is to approximate this value function in a way that is more manageable for mathematical optimization. Another idea in approximate DP is to retain the value function not for the state itself, but for the state after an action is taken. Since the number of actions determined by mathematical optimization increases exponentially, Defining the state after an action and retaining the value function for its features helps prevent memory explosion. This table compares DP, RL, MPC, and stochastic optimization in terms of models, predictions, value functions, optimization, value function approximation, and affine adjustable recourse variables. By taking the best aspects of these methods, it is possible to develop hybrid methods tailored to specific problems by making predictions about future events, performing appropriate value function approximations, and incorporating the proper optimization internally. One such method, which I have designed, is called MOAI hybrid, where mathematical optimization is combined with various machine learning methods and integrated with reinforcement learning. First, predictions of future parameters, problem instances, and solutions are made based on past problem instances and context. Additionally, value functions are defined for both post-action states and pre-action states. Furthermore, mathematical optimization is applied repeatedly in a rolling horizon manner to finite period problems, considering uncertainty through stochastic or robust optimization. Naturally, since similar problem instances are repeatedly solved, speed enhancements through the integration of machine learning and mathematical optimization are incorporated throughout. This diagram conceptually represents the approach. Considering a dynamic environment, we focus on decision-making at the current time, t. As shown in the lower left, ML is used to predict future parameters, problem instances, and solutions based on past problem instances and context. Finite planning period optimizations are performed using stochastic or robust optimization. Information beyond the planning period is approximated using value functions, and solution stability constraints are added, similar to MPC. As the overall method is complex, I will explain it in parts. The MOAI hybrid consists of 7 components. The first component is predictive ML. Assuming that problem instances have occurred up to period t, the parameters for future periods are predicted based on the problem instances up to period t. Uncertainty is also predicted simultaneously. Variables with a tilde are random variables. Additionally, features of each period and contextual information, such as weather forecasts, can be incorporated into the predictions. The second component is problem instance generation (ML). This component predicts and generates not only parameters like demand but also the problem instances themselves, with the aim of generating problem instances when the future context is known. When instance similarity can be defined, the k-nearest neighbor method can be easily applied. Other approaches, such as decision trees or deep learning, can be considered depending on the problem instances. The third component is optimization. Since the periods are not independent, multiple periods are optimized simultaneously based on the realized values for period t and the predicted values up to period t. When uncertainty is present in problem instances, stochastic or robust optimization is used. In such cases, affine adjustable recourse functions can also be used. Information before period t or after period t is approximated using a value function for the state. The fourth component is the state. The state is used to handle information outside the planning period. The value function, v, representing the expected profit from the state onward, is learned via simulation. The actual optimization is performed by maximizing the sum of the profit v, x, directly obtained from action x and the learned value function v, s, for the final period state s. Note that there are 2 states to consider, the post-action state and the state after a random event occurs. Decision-making can be divided into here and now variables determined before the random event and recourse variables adjustable after the event. For example, in delivery planning, the number of trucks decided the day before is a here and now variable, and the route determined after the day's demand occurs is a recourse variable. Whether to retain the value function for the post-action state or the usual state depends on the problem. In delivery planning, if the goal is to evaluate the remaining number of trucks available this month, the value function is defined for the post-action state. If the goal is to evaluate the carryover to the next day, it is defined for the usual state. The fifth component is speed enhancement through the Encode-Decode method. By learning from past problem instances and solutions, the solution speed for problem instances after period t is improved. Applying the Encode-Decode method is effective when many stochastic optimization problems must be solved to estimate the value function. The sixth component is the rolling horizon approach. This involves shifting the optimization from period t to period t sequentially. Simultaneously, predictions and states are also updated. The final component is solution stability. In practice, optimization must include penalties to prevent solutions from deviating too much from previously planned solutions. Penalties are set high for periods close to the present and lower for periods further in the future. When designing various MOAI approaches, a key factor is the concept of similarity between problem instances. A problem instance is a problem with specific numerical values. In general, the components of a problem instance can be broadly categorized into numerical data, structural data, and hybrid types. Numerical data that can be expressed purely through numbers is referred to as tabular data, which can be converted into multidimensional vectors. Structural data includes graphs, coordinates, and family of subsets. Hybrid types involve data where parameters are added to the structure. When the structure is identical and only the parameters change, similarity can be defined using an appropriate distance measure. A desirable measure would satisfy non-negativity, symmetry, the triangle inequality, and be zero if the two instances are identical, making the use of norms a natural choice. Here, we demonstrate the use of Minkowski distance. Correlation, Pearson distance, or cosine similarity can also be employed. If the structure of the problem instances is represented as sets, distance measures applicable to sets can be used. For two sets, A and B, methods such as Jacob similarity, the Srenson coefficient, the Tversky index, and the intersection coefficient can be considered. Regarding the similarity of general graphs, various studies have been conducted. Graph isomorphism or subgraph isomorphism determination is NP-hard. However, when the nodes in the graph are invariant, a distance measure, called graph edit distance, can be defined. Although this is also NP-hard, both are implemented in the Python library NetworkX. In recent years, research on calculating graph similarity through deep learning has become active, with methods generally divided into embedding-based, graph neural network-based, and kernel-based approaches. Finally, let's consider the method for calculating similarity between general problem instances that possess both structural and numerical data. A simple method involves converting problem instances into distributions, such as histograms, and calculating the distance between distributions. There are various methods for calculating the distance between distributions, but using transport distance is straightforward. Libraries like POT and COOPS can be used for computing transport distances. Direct application of optimal transport can also be effective for certain problems. Suppose that a distance can be defined between the components of one problem instance, e.g., nodes, and those of another problem instance. The cost of transporting the weights defined on these nodes from one problem instance to another can be defined as the distance between problem instances. As shown in the figure, this method can be used even for problem instances with different numbers of nodes. Assuming that the distance between problem instances can be calculated using the transport problem, it is possible to calculate the optimal transport quantity gamma between the components of the problem instances. Now, suppose the solution is expressed by variables defined between the components. If there are k similar problem instances for a new problem instance I, the solution for problem instance I can be constructed by weighting the solutions of the similar problem instances using the optimal transport quantities. Let's consider an example of a scheduling problem. The components of a scheduling problem are jobs and machines. Suppose that distances are given between jobs and between machines. Variables represent the assignment of jobs to machines and the precedence relations between jobs. For a new problem instance I, k similar problem instances are identified, and by solving the optimal transport problem for the jobs and machines, the optimal transport quantity gamma for jobs, or machines, can be obtained. The solution for the new problem instance I can be derived by summing the solutions of the similar problem instances weighted by the optimal transport quantities. When a distance between problem instances is defined, it becomes possible to construct a solution for a new problem instance from the solutions of similar problem instances. Additionally, clustering of problem instances becomes feasible using distances. When context is provided, it is possible to create a decision tree for classification into clusters. By assuming that problem instances contained in the leaves of the decision tree are randomly generated, it is also possible to use contextual probabilistic optimization. Finally, I would like to discuss the application of MOAI to real-world problems. Here is a classification of models and methods when optimizing a single problem instance using conventional approaches. Models are generally classified as deterministic or uncertain, and as static or dynamic. The most common optimization is deterministic and static. When deterministic and dynamic, it becomes online optimization. In cases of uncertainty and static conditions, stochastic optimization or robust optimization is employed. When dynamic and uncertain, candidates for methods include multi-stage stochastic optimization, reinforcement learning, approximate dynamic optimization, and model predictive control. On the other hand, in the MOAI world, it is assumed that there is data on past problem instances, and that optimization is performed repeatedly. In deterministic and static cases, optimization can be accelerated based on learning from past data. MIP-Learn and the Encode-Decode method are potential candidates. Even in deterministic and dynamic cases, automatic algorithm selection can be performed through online learning. In cases of uncertainty and static conditions, after making predictions from past data or auxiliary data, contextual stochastic optimization can be performed. Alternatively, predict then optimize or end-to-end learning, which directly computes solutions from data without going through predictions, can be employed. When dynamic and uncertain, MO hybrid, which combines mathematical optimization with reinforcement learning, can be used. MOAI deals with sets or sequences of problem instances, rather than solving a single problem instance. MOAI is considered effective when the sequence of problem instances meets the following conditions. First, it must involve large-scale problems with small solution errors and short response times. If these conditions are not met, conventional optimization of the new problem instance is likely sufficient. Additionally, there must be a sufficient number of problem instances with similar structures. If there is insufficient data, machine learning becomes ineffective, and learning does not help with completely different problem instances. This diagram illustrates when the MOAI approach is effective. The red arrows indicate that MOAI becomes more effective as they move to the right. First, from the perspective of response time, conventional optimization is suitable for logistics network design or planned delivery routing, which can be handled by batch processing. On the other hand, power flow optimization, dynamic delivery routing, and rescheduling, which require real-time responses, are suitable for the MOAI approach. From the perspective of problem instance similarity, production planning for made-to-order products is more suitable for conventional optimization due to low similarity, whereas production planning for consumer goods and unit commitment problems in power generation are more suited to MOAI due to high similarity. The amount of data varies depending on the target company, but generally, when problem instance similarity is low, more data is required. Let me touch on recent trends in the application of optimization. First, the size of problem instances is increasing. The reason there are few success stories in large-scale optimization is because they are unsolvable, but it is assumed that the size of problem instances that we truly want to solve is continuously growing. At the same time, the scope of models is tending to expand. For example, there is a growing need not only for logistics network design but also for simultaneously solving production planning, scheduling, and delivery route planning. Furthermore, the quality and accuracy of the solutions demanded by clients are improving, response times are getting shorter, solution frequencies are increasing, and the amount of stored data is growing. These trends are believed to increase the necessity of MOAI technologies. Next, I would like to introduce the current status for each individual application, starting with delivery routing problems. Using well-designed metaheuristics, it is possible to derive solutions with a few % error for problem instances with around 10,000 customers. On the other hand, mixed integer optimization solvers are limited in their applicable size. For simple time window benchmark problems, up to about 200 customers can be solved. When there are many constraints, a column generation method using beam search or dynamic programming as subproblems can solve problem instances with up to 300 customers. When using constraint optimization solvers, exact solutions can be derived for problem instances with up to about 100 customers. When solving problem instances with around 10,000 customers, the bottleneck can be the generation of travel time data. Calculating the shortest paths for 10,000 squared, i.e., 100 million routes, costs approximately $400,000 using Google Maps. The frequency of solution is usually about once a day, but in cases like convenience stores, plans are made in batches every few months. When rescheduling, response time is short, and speeding up is necessary by fixing part of the solution. In dynamic and stochastic delivery planning, it is necessary to solve multiple scenario-based problem instances in real time. If the similarity between problem instances is high, MOAI becomes effective. Consider the application of MOAI to long-distance delivery planning under dynamic and uncertain conditions. This is an example of full truckload, FTL, where full loads are transported over long distances. Suppose the plan for day T is created on day T2. Based on demand forecasts at this point, routes, prices, and the number of trucks is determined. Here, only the number of trucks is an immediate decision variable, while others can be modified later as recourse variables. As shown in the leftmost figure, the current optimal solution involves transporting goods along the orange line with 2 trucks, with backhauls indicated by the dashed line. The blue dotted line represents potential demand, which may arise by changing prices. After one day, on day T1, the price for the blue goods is lowered. As a result, some demand arises. As shown in the middle figure, the backhaul, indicated by the solid line, reduces empty transport and increases profit. After another day, on day T, the price for some of the blue goods is further reduced. As shown in the rightmost figure, the most profitable route is selected based on the arising demand. The number of trucks remains 2, but profit increases by adjusting prices and routes. Let's consider the dynamic and uncertain nature of parcel delivery. Assume there are confirmed customers, represented in black, and probabilistic customers, represented in white. As shown in the top left diagram, a truck must decide which of the 2 confirmed customers to visit first. Confirmed customers are those that need to receive a delivery today, but they might not be at home. If the customer is not at home and the visit occurs before the 1900 hours cutoff time, a delivery notice will be left. In such cases, as depicted in the top right scenario, the redelivery request may either be scheduled for a specific time or deferred to the next day. As shown in the bottom left diagram, if the truck first visits the upper confirmed customer and they are at home, the truck can return to the depot along the shortest route, indicated by the gray line. However, if the customer is not at home, the redelivery instruction is determined probabilistically, and the customer is reclassified as probabilistic. If a time-specified redelivery request is made, a second visit will be necessary, following the red route. On the other hand, as depicted in the bottom right diagram, if the truck first visits the lower confirmed customer, the delivery time to the upper customer will exceed 1900 hours, making redelivery impossible, and the delivery will be deferred to the next day. Optimization techniques using MOAI are already being applied in the power industry. For example, the unit commitment problem of power plants can be solved within a few hours using mixed integer optimization solvers, achieving solutions with only a few % error. Of course, the accuracy and time depend on the size of the problem instance. In the United States, where integration and scale have advanced, this level of computation time is necessary. These computations are performed several times a day, and since the problem structure remains almost the same daily, improvements in speed and accuracy can be expected with MOAI. There is even a successful case where MIP-learn was applied. For the power flow problem, a nonlinear optimization solver can be used, but real-time response is required. Since the problem structure is almost the same, there are cases where optimization proxies have been used for real-time control. In production scheduling, specialized meta-heuristics can solve actual problems involving resource-constrained scheduling for 100,000 jobs within a few hours. In research, many specialized solutions focus on benchmark problems for job shop and flexible job shop scheduling. By using reinforcement learning packages specialized in combinatorial optimization, slightly better solutions than dispatching rules can be obtained for benchmark instances. If there is sufficient data and a high degree of structural similarity, speed improvements with MOAI techniques can be expected. Finally, let's discuss the application to shift optimization. Currently, most shift optimization cases are small-scale, and many do not even involve optimization. Small-scale optimization for individual stores can be done relatively easily, and feasible solutions can be generated using free tools like Pulp or CPOpt, or even ChatGPT. However, in cases where there are over 100 staff members, 30-minute intervals over a month, and consideration of work including breaks, proper optimization becomes necessary. In rescheduling, short response times are required, but if only part of the solution is to be changed, reoptimization with fixed variables can be applied, and if there is sufficient data and high structural similarity, MOAI techniques can be applied. Now, let's summarize the key points. In this presentation, I first proposed 7 classifications for the field of machine learning and mathematical optimization integration, MOAI. These classifications are not exhaustive but serve as a convenient guideline. MOAI has been studied independently across various fields, and moving forward, cross-disciplinary collaboration will be essential. I also proposed a new framework, Encode-Decode method, that uses past problem instances and solutions as teachers. Additionally, I introduced a new framework, MO-Hybrid, for dynamic optimization models. I highlighted the need for fundamental research on the distance and similarity between problem instances and provided some basic ideas. Experimentation and application of these methods to real-world problems remain as future challenges. Lastly, I would appreciate it if practitioners who repeatedly solve optimization problems could store many instances and solutions.